This video is on entropy, enthalpy, and Gibbs free energy. And what this video is really all about is why do some things happen? Why are some things thermodynamically favorable? And what that means is why is it if you put equal amounts of reactant and product in a reversible reaction, okay, if you do that, in some cases you end up with more product, in some cases you end up with more reactant. If it's favorable, you end up with more product. Now, whether something's favorable or not does not have anything to do with how fast something happens. They used to call it spontaneous, and that would confuse things. What this has to do with is, will reactants turn into products? Rusting is very thermodynamically favorable. It's really slow. Blowing up a firecracker is very thermodynamically favorable. It's very fast. Thermodynamically favorable means the reactants will turn to products, and if it's an equilibrium situation, you will end up with more product than reactant, and K will be a large value. So what are the two driving factors, okay, in these reactions? Well, the first one is something called entropy. And this is probably the first you're hearing of this, except for when I taught it in class. Entropy means essentially randomness or chaos. The best way to view this basically is that things tend to get more evenly distributed, and think about this in terms of phases. Okay, so solids are organized. Liquids are a little less organized, and gases are just like molecules bouncing all over the place. They are totally chaotic. All right, so you can think of this in terms of the phase, and that really kind of makes it easier. Okay, and systems tend to move towards this. So it's thermodynamically favorable if the delta S is a positive value, and that means it's getting more random. So as long as we keep in mind that solids have the least amount of entropy and gases the most, it's pretty easy to figure out what's happening in any situation that you're ever going to be asked about. If it's complicated, you can actually look up the values, which is what my students in AP Chemistry need to do, but you do not. So here's what you need to know. Since liquids have more, if something's going through a phase change that's turning from a solid into a liquid, since liquid has more entropy, the delta S here would be a positive value. Since gases have more entropy than solids, this would also be a positive value. What would have a negative value? Well, something that was the opposite direction. So let's say you had something that went through what's called deposition. So when you make snow, you go from a gas, back to a solid. That has a delta S that's a negative value. Or if you were to go from a liquid to a solid, that would also have a delta S value. It was negative. All right. Now, if it's a chemical reaction, you have to kind of look a little bit at things. So if it's a chemical reaction like the one down below here, sorry, I'm just cleaning up this mess I made. All right. So if it's a chemical reaction like this one right here, the only thing you'd ever be asked to do is to look at the equation and count moles of gas. Gases have so much more entropy than the other phases. All you have to do is count the moles of gas on the two sides. Whichever side has more moles of gas has more randomness. Right? So if you have like this reversible reaction here like this, okay, you have 2 moles of gas on this side, and while you have this 3 right here, this is a solid, okay, and this is a gas. So looking at the phases is critical here, right? So you have 2 moles of gas on the left and 1 mole of gas on the right, and I really don't care about the solid. The fact that I have less moles of gas on the on the right over here means that I have less randomness on the right, which means in this direction, as we go this way, delta S is a negative value. Now, dissolving like the NaCl solid to AQ is always going to have a positive value. Whenever you dissolve something, AQ is always more random than solid. So, general rule, as you go towards gases, entropy increases. As you go towards AQ, entropy increases. If you have gases on both sides, count the number of moles of them. More moles on the right, entropy's up. Less moles on the right, entropy's down. That's really it. Now, systems that are thermodynamically favorable tend to have 2 properties. They are either they have entropy increasing and they have enthalpy decreasing. And this is really annoying because the signs are opposite, right? And students tend to put the 2 things together, but they're not the same thing. Okay? Entropy is randomness. Enthalpy deals with the energy that's released or absorbed during the change that's occurring. Right? And it's a comparison in the potential energy of the reactants and the products. So in a situation which is exothermic like this versus one that's endothermic, okay, a reaction that would be automatically spontaneous would be something which now this is exothermic, so delta H here is negative, and this has delta H positive. A situation that was exothermic and which you went from a solid to a gas, So the delta S is a positive number and delta H is negative, is definitely going to be favorable. Okay? The always not favorable situation is one in which it's an endothermic process, so delta H is positive, because this, okay, having more energy is just not favorable, right? So things tend to lose energy, right? Balls roll down hills, okay, firecrackers explode, okay? Things tend to move towards lower energy. Exothermic things tend to be favorable. Also, the exothermic things that produce more gases are also usually favorable. So if you were to go from like the gas to a solid here, okay, in which the delta S was negative, this would definitely not be favorable. All right. Now, some things have the same signs. So we're going to talk about that, and those things that have the same signs are going to be temperature dependent. Okay. So you can just kind of memorize if the delta H is negative and delta S is positive. So if it's exothermic and entropy is increasing, favorable. If it's endothermic and entropy is decreasing, not favorable. Okay, and you should be able to recognize when somebody's exothermic by where the energy is in the equation, or looking at a potential energy diagram, or looking it up in table I, right? On this page, what you have is Gibbs free energy equation. Now, again, this is really not on the regents, but it's really a summary of everything and kind of maybe a helpful way to look at it. If delta G is equal to 0, it's at equilibrium, okay? Right, so delta G equals 0, it's at equilibrium. Okay, if delta G is less than 0, then it is going to, that means it's favorable, and that means sorry, I'm just gonna do this. Okay, good, got that on there. Sorry about that. It does that sometimes in this program for some reason. And if delta G is greater than 0, it's not favorable. All right. All right. So we can look at the sign convention. So when is delta G always going to be favorable? Well, if the delta H is negative, okay, and the delta S is positive. Now, temperature is always in Kelvin. So I'm not going to put this in. I'm going to leave this line blank. But basically, positive times this negative right here would be negative. And a negative plus a negative would make delta G always negative. And when delta G is less than 0, it's always favorable. So if the signs are opposite, it's either always favorable or always not favorable. As long as you can remember one of them, you're kind of good to go. Like if you remember, when delta S is positive and delta G is the opposite, it's going to be favorable, you're good. The other situation that is a definitive situation is one where you have delta H is positive and delta S is negative. When delta S is negative, a negative times a negative is a positive. If you add a positive to a positive, delta G has to be positive. So whenever a situation is that delta G is positive, it's just not favorable. Neither one of these forces, enthalpy or entropy, can possibly drive this reaction. All right? Now, for the last two, the sign for all phase changes, the signs are always the same. So, for example, when you're going from a solid to a liquid, entropy is increasing. So, for this phase change, the delta S is positive, okay, and this is endothermic. The heat would always be on the left here. This is melting of ice, right? So they're both positive. Now, what's the situation with something going from a solid to liquid? Well, you have to get above 0 degrees Celsius. Okay, so when they're both positive, you have to get above a certain temperature. For melting of ice, it's 0 degrees Celsius. If this was boiling water, it would be 100 degrees Celsius or 373 Kelvin, right? So this is temperature dependent, right? Because one factor says, yeah, let's go, because entropy is increasing. But the other factor, the endothermic thingy, the enthalpy says, no, don't go, right? So they're kind of both pushing in opposite ways. So in this case, we say at a certain temperature, entropy can drive the reaction, okay? But you have to get above that temperature, right? In the other situation down below here, you get a situation in which it's an exothermic process, right? So this is a negative delta H. The heat's on the right, okay, because you're going from a gas to a liquid. That's exothermic. That's condensation, right? And you're going from a gas to a liquid, and liquids have less entropy. So in this case, entropy is decreasing. In this case, all right, if you want something to condense, you have to get below a certain temperature. So when it's negative, you have to get below a certain temperature. And you can think about what's driving these things, okay? So for in this row right here, what's really driving it is this. This is the driving factor. And the enthalpy is sort of blocking it. I mean, you get above a certain temperature, okay, this whole part of the equation becomes big enough to make the whole thing negative, right? Because positive times negative is a negative. On the bottom situation, the bottom row, right, the thing that's really driving it is the delta H. All right, that says go. That's thermodynamically favorable. But the delta S says no, it's not favorable, right? But when the temperature gets low enough, the value of this whole T delta S thing gets smaller than the negative value of delta H. And all of a sudden, the delta G can be negative, right? Because negative times negative for this is a positive, right? But when you get below a certain temperature, the negative delta H is bigger than the positive thing for the T delta S. And so this is also temperature dependent, but you have to get it below a certain temperature. So quick summary, when delta H is negative and delta S is positive, always favorable. When delta H is positive and delta S is negative, never thermodynamically favorable. If they're both positive, raise the temperature. If they're both negative, lower the temperature. If something's at equilibrium, delta G is 0 because both the forward and reverse reaction happen at equal rates. Okay? And by the way, this is the lowest energy state when you get to equilibrium. That's why things always move towards it. Done.